Okay, good morning, everyone. Thanks for your patience. Thanks, Gerrie. Here I go with your introduction. So after leaving school, which was Grey College in South Africa, Gerrie studied at the University of the Orange Free State under some very well-known names, Willem van Biljon and Ben Boert in particular. And as a geology student, he started underground work at, some of us will know this, the President Brand Sec of Two Shaft in Welkom, working for a well-known Anglo-American consultant, Tony Knowles. Anyway, he worked as an exploration geologist then for ISCOR for nearly 3 years, but resumed an academic career in 1975 with a PhD under Henny Blino and Alwyn Strock, again back at Free State. Subsequently, he joined the Anglo-American Seismic Research Unit, headed by an extremely lovable and great guy, Dave Ortlip, in 1985. And since that time, he's been one of the sort of busiest and leading guys in his career in the Institute of Mine Seismology, with offices in Hobart and Somerset West. So, Gerrie, we look forward to your presentation today. We're going to talk about some great characters of the mine seismology services and people that did some tremendous work. And over to you.
Thanks, John. It's a bit of a funny subject to talk to geologists about. My experience overseas is that geology and geotechnical departments are one. In this country, it's completely divorced, and the Rockies report to the mining guys, and the geologists, I don't know who they talk to, to God, I think. But so they're in different worlds, and it's a pity because there's such a lot of common ground. So I'll be talking about some of the people, but I'll mainly be talking about rock failures, and there'll be 1 or 2 slides about the future. So it's my subjective views, and I will surely leave out some important names. So sorry about that. So we're kind of stopped going deeper. In the good old days, the future was exciting. We were forever going deeper, and there was nothing to stop us. And then it kind of stopped. And the question is, do we still have the guts to go mine deeper? There are maybe some positives. There are two projects going currently. One by Harmony. That's the preconditioning by blasting, and the one is a hydrofrac one by Sibanye. And the idea is to precondition old pillars, because there's a lot of gold there, and then mine them, soften them and mine them. And if they're successful there, they can probably then use that same technology and go deeper, because in several overseas mines, the fundamental solution to large seismic events is preconditioning by hydrofrac. The people and the institutions were really great. A useful reference to all of this is Ray Durheim and Kevin Riemer's paper, which you will see there. This is from a newspaper, Financial Gazette, 1964. And you see big names there. And that's a nice little piece of text there. It's perhaps ironical to note that despite the fact that the Stone Age preceded the Bronze Age, the science of rock mechanics is today many years behind that of metal technology. That's probably still true. They were doing really good stuff. Neville Cook was underground. He had the seismic system installed. This is now in 1964. I mean, this is way back. And he found that these seismic events were close to the face, which is important. Nowadays, with our mine seismic systems not always in the best state, you get a bump and the plots maybe 40 meters or 50 meters in a hanging wall or footwall, and the guys are happy, say, well, you know, it's not our fault. This is something, an act of God or something, which is untrue because the events are actually close to the face. And then in the article, they refer to Ryder. So there we have 5 big names in that 1964 article: Cook, Hooke, Ortleb, Schalleman, and Ryder. Cook refined this concept of energy release rate, which is a very important measure of this potential for rock bursting ahead of the mining phase. And it was well published, or well put together in this landmark paper in 1966. You see Cook's name there, Hooke. I don't know who Pretorius is. Then there's Ortleb and Schalleman, applying rock mechanics theory to rock burst studies. Cook went on to become an internationally well-known rocky. That was like a handbook of rock mechanics for many years. Everett Hooke is still well known for consultancy work, mainly in civil engineering. Ryder is still with us, and he stayed on, and he wrote a very important paper called about excess shear stress. So while ERR was kind of telling us about the seismic hazard directly ahead of the face, the excess shear stress told us about the seismic hazard along geological structures. And then these 2 books came from Ryder and Jaeger. These are basically currently the Bibles of rock mechanics in this country. And then Ortleb wrote this fantastic book, which is published by SAIMM, and it's for free. You can just download it, or if you want it, I can have a copy. It's a fantastic book about observations underground, and I will quote from that book right now. Schalleman was initially involved in coal only, but he became involved with the hard rock mines. And he published a very important paper in 1993 in RASM 3. I will talk about RASM in the last slide in this section. That is now a theory of modeling rock bursts. Okay, his ideas were picked up by a Russian called Linkov, and in RASM 8 he embroidered on that theory. And lately, the guys from IMS picked up on that, and they've now developed the Schalleman-Linkov method, combining the theories of these 2 guys to simulate mining-induced seismicity. This is very important, and I'll talk about it briefly now. Then I must introduce John Napier. He was at Mining Tech for many years, and now he's at University of Pretoria. And he came up with this limit equilibrium method to model non-elastic failure via elastic mode. And that gives us the capability of now modeling shear failures on structures using the ESS concept of Ryder and Schalleman and Linkov, and the crushing ahead of the face by his limit equilibrium method. And that's been picked up by Jacques Gerber from IMS, youngster. And here he combines it into one massive code in which he uses the LEM method of John Napier to model the crushing ahead of the face, and he uses the Schalleman and Linkov methods to model failure along shear zones. And since these shear zones, these Ortleb shears, which I'll talk about in a while, evolve in solid rock, you don't need a pre-existing structure. So he can model them, and he can create these structures in his model automatically, and he can include geological structures. And now he's got everything together, and he can model as mining progresses, you can see there's mine layer, there's a dip pillar and stopes going out like that. And you can model these autopsies and face failures in one package. And you can come up with this kind of correlation between modeling the observed seismicity, modeling seismicity, and compare that with observed seismicity. Now, since we cannot predict these large events, this is very important because we can predict the mining. We know where the mining goes, we know at what rate they will mine, we know where they're going to mine. So you can take this method and model forward and get some idea of what the seismic hazard will be for a given mining area for a given time of interest. That's a very, very important way to go forward with seismic hazard assessment in mines. Okay, back to the names. There was no Jochen. He was one of the earliest guys to do seismic measurements in mines. Nick Gay is a geologist. He pioneered strain analysis in South Africa. He joined the Comro. He built physical models of stopes in concrete blocks, and he pressed the blocks and he looked at the shearing area of the face. This is fantastic work that he did. Chris Reuring was a geologist from Rau, and he got involved with Comro for a while. Art McGraw was the first true seismologist involved. He was at BPI Geophysics, and he can be called the father of seismology in South Africa mines. And then Steve Sporriswood, he's with us, of course. He's a well-known local seismologist, and he runs his own code as well to model seismicity. Rod Green, a friend of mine, he's an electronics engineer with PhD in seismology, and he's one of those guys that can make a seismic system with a tongue-nested blow graph. Horst Wagner is an important guy. He was heading Comro for a while. Sander Boudevari was a famous teacher at Wits. I'll talk about him in a second. And Richard Brummer did great detailed mapping of fractures around deep level stopes for his PhD at Rau and the Chris Reuring. That's Boudevari's book. It was also for many years the Bible of rock mechanics book until Jaeger and Ryder brought out their books. Sherman Boudevari came from Hungary. They escaped Hungary after the Russian invasion of '56. Sherman came straight to Johannesburg. Boudevari ended up in Adelaide, and apparently one day, and he was offered a full-time professorship, but based at Broken Hill. And he didn't like that because he read about the fact that Broken Hill had the highest incidence of teenage pregnancies in Australia. So he decided to come to Joburg. More names. Dick Stacey is a well-known geotechnical engineer, and he wrote a really fantastic paper on extension fractures, explained them. Paul van Heerden was a geologist, and he was managing a seismic system at Stilfontein. Van Zyl-Brink and Peter Mountford, they initiated predictions, Rockburst prediction, which is still something that we all would like to do. Terry Hagen looked at structures using a box with two cameras in, and he had some stereoscopic pictures developed, and he looked at this stuff. So he was the first guy who did photogrammetry underground here. All these names, they were pillars of the industry, establishing rock mechanics as a profession in the mines. Rudy Kirsten was a geologist. I remember him, one of the famous things that he did is to develop a tunnel, allow it to deform, crash, and then he could develop a tunnel next to it because the ground was distressed, and the second tunnel was then easy to use. Tony Jager was working at Comro, and he is co-author with Ryder on these books. Mark Hilder did modeling of wave propagation around stopes, and Matthew Handy is his father was a geologist. He came up, I think he started with the geology degree, but he got into rock mechanics, and he wrote a book on theoretical mechanics of professional practice, published by the SAIMM. Then there is Hiroshi Okasawara from Kyoto, and he's been involved in seismic systems in South Africa for a long time. all these papers and reports that he did. There he's pushing a piece of granodiorite with a Ishi strain gauge in. It's on a visit to Japan, and you can see how the strain is recorded on this instrument here. So extremely sensitive strain gauge. So these Japanese did a lot of work, many projects, many drilling projects and so on. And it was difficult, it was expensive, happily mainly for the Japanese taxpayers. And the success was mixed. Many hundreds of reasons. To do research underground in our minds is really, really difficult. Things go wrong all the time. But they enjoyed, and they wrote some fantastic papers, and the best of them all in my eyes is this one. I don't have time to explain that, but it's fantastic work. There was a Polish invasion. Alex Mendeski, my boss for many years, he started under Dave Otlep. He started mid-85, I got there end 85. And he drove the development of commercial seismic monitoring systems, established in the company ISI, which then morphed into IMS. And he's a world expert in seismic hazard. And partly due to his presence, these guys came. Andrzej Kiko, he's at University of Pretoria still. Artur Cikowicz is back in Poland, as far as I know. Ted Stankiewicz is in Klerksdorp still, and Stefan Glazer is retired in Palabora. And these Polish guys also like to write books. There's Andrzej Kiko with Gibowicz. There's Stefan Glazer. And there's this book where Alex was the editor. Came out of a research project that we did. And there's a book that's online available, Mine Seismology reference book by Alex. And if there's time, I will come back to that picture at the end of the talk. For organizations, Comro, of course, WITS and BPI Geophysics did great work. The seismic system, the seismic research unit where Alex and I worked. SIIM, I mean, it's fantastic to have such an organization in this country. And all the publications are open file. It's really, really excellent. And then SANGOM is like what the Geological Society is for us. SANGOM or SANAIR then is for the Rockies. That was just going back to Comro from Chris Röring's obituary. He worked at Comro with Neville Cook, Nick Gay, Neil Jochen, Miklo Sherman, seismic brittle and brittle rock fracture research and deep and gold mines in South Africa is unparalleled, and Comro was a school in that. I mean, this is just fantastic times that they had. That's Comro 1985, some of the names. Horst Wagner, Scholleman, that's Gay over there, and Noel Jochen, and the other names. And I know Stewart over there, Dr. Stewart, also did some work with Dave Otlep. That is SANAIR. And they did, they're quite active doing all kinds of, annually at least one major conference. And they've been doing this since 1972. The focus is not necessarily always on rockbursts. But an important one that they organized with SAIMF is the first international symposium on rockburst and seismicity in mines, which they brought Gibowicz in. They also brought, over the years, big names like Fairhurst, Brown, Goodman. These are big names in rock mechanics, and Gibowicz is a big name in mine seismology. Today, the rock mechanics in the gold mines are addressing the rockburst problem mainly by design. The trick is to minimize the softening of the loading system without sacrificing too much gold in the pillars. You can see over there, there's a stage where longwall mining was applied, and you can see that modeled closure. And down here, where they've introduced the pillars, the total closure is much reduced, and that by reducing the closure, you're reducing the seismic hazard. Also, very important is support. Support is the second line of defense. It's a major cost item on the mines. So it's very important to develop and study and research the support systems to maximize the efficiency, to contain the damage, and to minimize the cost, because it's very expensive. That's a friend of mine, JJ van Aswegen. He told me he was sitting in this waiting place when this rock burst occurred, and he could see this wall of rock moving towards him. But it was captured by this fantastic support system, wire mesh and lacing, and he survived. So, to a large extent, the rock engineering departments focus on design and support, leaving the seismological monitoring, analysis, and interpretation to generally outsourced mine seismologists. The RASMs, the first one was a fantastic one, 1982, brought in big names. These are all big names in crustal seismology: Barth, Blake, Leighton, Genswell, Tom Hanks, not the actor, Jim Rice, and George Gibowicz was the leading mine seismologist guy at the time from Poland. There were many RASMs subsequently. It was the first one organized by Nigay and Wainwright. There was 88, Charles Fairhurst, 93, Paul Young, and so on. The best one was this one, 2013, where we all got on a boat in St. Petersburg and ended up in Moscow. And during those 5 days, we had this fantastic conference. Okay, so that is the first part of the talk. I would like now, so that I think I will do the second part now, and then we will carry on. Then we can stop for questions. Let me just see, where am I? Just 1 second. Okay, so this will open in a second, I will hope. Okay, can I get some feedback? Is everybody still with me?
Yeah, that's good.
Okay.
Yeah.
Okay. Thank you. Okay, so now we're going to talk about forensic studies of rock bursts. We can talk about fault slip events. Just 1 second. No. Okay, so that's those fault slip events are the real earthquakes. Then there are the rock bursts, which are the smaller events closer to the face, and then there are hybrids, of course. Now, most people dying from rock bursts in mines are from the smaller ones, the real rock bursts. So we focus on that, and then later on we'll talk about the earthquakes. So that's Dave Ortleb at one of his favorite photographs. In this photograph, you see a stope that closed dynamically, punching a steel support unit into the footwall. That was today a very important indication of the velocity of closure. Okay, most likely we're talking about 2 meters a second or something like that. Very fast dynamic closure. That's the last time I went underground with Dave in 2007 at Daytona. So, when we talk about these forensic rock burst studies, we mainly talk about the exhumed structures that we can analyze. We can look at them, we can photograph them, map them. And Dave was absolutely an expert on that. He basically initiated that kind of study. Koos Bosman and I tried to do some of that too. Then, of course, associated with that is the seismic data analysis, and that's mainly sitting in front of the computer and trying to sort out what the seismology is telling us. And then you have to try and put it all together so you can explain what really happened. So there is a picture of one of these shears that they've mapped. This was the classic claims, West Claims #1 pillar. Because of the pillar was highly stressed, they mined the pillar, they had many rock bursts. A description of these shear fractures was published by Gay and Ortleb in 1979. And it's now well described in Dave's book. And he gives a story there about how important it was to convince the mine manager to actually develop 90 meters of tunnel to actually map the structures. Okay, so this is what the tunnels look like. This is two views of the same tunnel system. That's a plan view, and these are all the intersections that they have of the Ortleb shears. So that's from one of those tunnels that they developed. There's a shear over there, and there's another one there, and this is what it looks like. There's just a small section of an Ortleb shear. Can you all see my mouse as I move it around?
Yep.
Okay, good. So there's the tip of the shear. In that position, you can see the direction of shearing. That's the Ortleb shear over there. This overshoot is important. If you look at that structure, you can say, okay, now we understand the slip direction. It's clearly normal slip. But where did it initiate? What is the direction of rupture propagation? In this particular case and others, the best evidence of the direction of rupture propagation is the fact that you have overshoot. In that area there, it's impossible for that structure to yield in a normal slip fashion because there's an opening below here. So the rock wants to move into the opening. So if anything, you should have reverse slip on such a structure. So to find that structure in that position relative to the stope means it had to come from below. It had to move in this direction. And that helps us to establish the direction of rupture propagation. That's very important because what we now, from this kind of study and others, we discovered that the rupture always propagates towards the opening, which is bad news because it attacks the opening. It comes from some distance, either in the hanging wall or the footwall, but it runs towards the opening. And when it reaches the opening, if it daylights, it's this dance at nacht. If it doesn't daylight, you still have a bit of a chance. And with all that work, he managed to actually do 3D mapping of the structures. You can see two sets or two structures here. The one parallel to this face, moving in that direction, and the other one parallel to that face, moving in that direction. Always parallel to the face. And this is the picture you see, the stope face. And then you have this quite large displacement. 100 millimeters is a lot of displacement in this environment. And we'll come back to that in a while. And then, of course, we were starting talking about all these structures, and there was no consensus on terminology. Then Ortleb talked about the mining-induced fault zone, Magar shear zone, shear fracture, burst fracture, shear rupture, dynamic rock burst rupture, dynamic brittle shear. So in 2008, I wrote a paper and I said things right, and they're simply called Ortleb shears. And now everybody knows what we're talking about. They've listed definitive characteristics of these shears. Finely comminuted rock flour, very important. Then this relatively extensive near perfect planar surface showing a strongly textured lineated appearance like a greatly enlarged sharp-edged metal working single cut file. And it's also been described as a Haeckel surface. Shear displacement of several centimeters, pinna joints, and an acute angle. That last one is pure structural geology. It's nothing funny. So let's look at the strong lineation. This is the a no-tip shear. You can see there's one at the back there, and there's another one at the end of this roadway in a stope. They called them roadways at that time because they were doing trackless mining. So then there's a roadway. Normally it's just a gully. So this is a gully. So it's a gully running orthogonal to the face. The face is to the left. And there's two no-tip shears in the footwall. Again, overshoot because the displacement is right lateral. We see that in a second. You can see. Okay. I'll go back there. So the displacement is right lateral, and that cannot be in that position below the stope. There had to be an overshoot. What we see here is that the end of the gully broke away along the shear zone. So that surface we see, that lineated surface we see, is actually the wall of the shear zone. There's the no-tip shear 1 and the no-tip shear 2. This no-tip shear 2, the wall of the shear zone is this surface. And you see this very strong lineation. Later on, they advanced this gully, and we could see the no-tip shear completely. And you can see now that it is these extra extension fractures, the intersection of these extension fractures, which gives rise to this very strong linear fabric. So it's actually, from a structural geology point of view, it's nothing funny. It's just something that Dave Ortlieb was very much intrigued with. Yeah, in this case, we can also note that there's no breakthrough shear rupture, which I'll talk about in a second. It's right lateral displacement, extension fractures coming through, but the actual displacement is infinitesimal. So that's what I said. Now we go to breakthrough shear ruptures. This is where the powder comes from. You can see the white stuff. You can see where we have this white stuff, there's a small breakthrough shear rupture where there was actually displacement along. That's where the pulverization happened. We go back to that example. This can only happen, this kind of deformation can only happen in a stiff loading system. It's where the loading system is so stiff that it allows deformation without runaway deformation. When you have a loading system where strain energy is accumulated in the loading system, when that sample fails, this strain energy or this elastic strain energy is released, and it drives a dynamic failure. And in this case, we would have a breakthrough shear rupture. Here, because we are some distance ahead of the face, when the shear happens, we're in a stiff loading system, we don't have a breakthrough shear rupture. And just see something else. What we're looking at here are extension fractures, and the extension fracture happened exactly along the sigma 3, sigma 2 plane. Okay, so what we're seeing is a mapping of the stress trajectories through this shear zone. We have nicely curved stress trajectories and nicely curved extension fractures. This is something very interesting which I've been looking at subsequently. There's another case. You can see the extension fractures make a large angle to the shear zone. This is from an unpublished collection of photographs which I have from Dave. And at the largest, zoomed out, you'll see two shear zones. And you see the shear zones, the angle is not as it should be, not 60 degrees. It's much larger. That suggests, in the first place, a high loading system stiffness, because we don't have breakthrough shear ruptures. And it also says that the angle between the difference between the sigma 1 and sigma 3 is small to be able to get this kind of deformation. Otherwise, we would have the classical 60 degrees angle between the shear zones. The rock flower is very important. But first, let me introduce Zef Regis. I met him in Vienna once, and then later in Jerusalem, and over lunch, my stories about the structures in the mines maybe lured him to do research in our mines. He organized a workshop. He got big names in to come and initiate his research. There's Yura Ben Zion, the top seismologist in America. That's himself. That's Zef. That is Uwe Reimel. You will all know him. That is Tom Jordan, University of Southern California. That's Mark Zoback, also from Stanford, not Stanford here next to Hermanus. This is Stanford in California. That's Hiroshi Ogasawara. That's Ishii. That's a guy that builds those strain gauges. That's Steve Spottiswoode, Art Magar. That's Cesar Trifo. He was our competition before he retired. That's Malcolm Johnson. He can also build a seismic system out of nothing. There's Alex Medetsky and lots of other names here. Some important guys from Potsdam University, Japanese guys whose names I can't remember. That's Zef and Dave Underground. So, the rock flower. The old guys will tell you, if you walk into the stope after a rock burst, everything is white because of this fine rock flower which is everywhere. It's the product of an extreme strain rate. That's the big outclip shear which Zef called the Bosman fault in his publications. This is part of that shear zone, outclip shear. And what's interesting here is the semi-rounding of the fragments inside this powder. So it's this powdery rock material, and inside the fragments are rounded, or not completely rounded, but somewhat rounded. I took a sample, that particular sample, and I've got it in my desk. And these are two views of the same piece of fine-grained conglomerate or coarse grit, quartzite, whatever you want to call that. And you can see so it's a fragment within the shear zone, within the rock flower. And you can see it's around. There is a bit of slickened sides, and you have this rounded appearance. We'll go to another example case. This was at Tautona in a shaft pillar, a tragic accident. This stope face was completely closed by this event. The seismic event consists of two parts. The initial part is outclip shears ahead of the face, and the final component is this closure of the stope. And in there we have some additional shearing, which I'll zoom into that area now. So there it is. You can see this rock was all moving towards the stope below here. We actually in the hanging wall, and the stope is way down. And what you notice is, in this case, angular fragments. This deformation, this dynamic deformation, was dilatational, and there was no time for shearing and rounding of the fragments. That was the relative motion. There was some support unit containing that portion. So if you zoom in on that area, you can actually get reverse faulting. You can see reverse faulting because of the orientation of these extension fractures. And you can see that, but it's transtensional. So there's opening and shearing happening at the same time, and you see these rock fragments which are not rounded. They are in this these fragmentary fashion characteristics. That sort of reminds me of what we see in the cerataccolite. This is our classic exposure of cerataccolite. At Vredefort, you can see these rounded granite fragments drifting in the dynamic melt, which is cerataccolite. You have these ceratacolites all over the gold mines, and we see them in different places. This is Titona. This is basically a fault zone with cerataccolite in, and in the cerataccolite we have folds, sheath folding because of the extreme deformation. So this is a highly viscous fluid which is being sheared, and you get these extreme deformations. So this is transpressional shearing of the cerataccolite. But here at another mine, this is at Talekwa, the cerataccolite looks different. There's no flow structures in the cerataccolite, and the fragments again are not rounded. Okay, see there, the fragments are not rounded. So there's some similarity clearly between this dynamic deformation, which creates melts if you have the sufficient depth, maybe 5 kilometers or more, and the same deformation rate with Rockburst. And here we don't have melts, but we have powder like that. This is, I removed that shot glass in the first picture, and you can see a negative angle of repose to reflect how finely grained this flour is. You probably played with a flour on your mother's table when she cooked, and you could do things similar to that. So back to Zed then. So he took samples of the rock flour from the texture they refer to as the Boson fault, and it landed them a paper in Nature. There is particle size and energetics from gouge earthwork rupture zones in Nature. And basically, they concluded that the fine-grained gouge is not related to quasi-static cumulative slip, but rather by dynamic rock pulverization during the propagation of a single earthquake, because they found similar material in the San Andreas fault. So from that publication and others, we can conclude that the rupture propagation velocity is important to make the flour. And then, and you sometimes don't see it because of the slowness of slip. Okay, then if we look at the powder again, the fragments, the large volume of very small fragments increases the surface area by orders of magnitude. Now, to create the surface energy, the surfaces, you consume a lot of energy. Okay. Also, the powder provides lubrication, so there's zero frictional, basically zero friction on that moving structure. So again, you don't build up frictional heat. So this kind of, this could be used as to explain the lack of heat anomalies. One would expect, because of the frictional heat built up over these fault like the San Andreas, you would expect a heat anomaly, and they're not there. So maybe this is the explanation for that. Also, they concluded that the rupture is the dominant process, and there's a lot of research done on friction. they build huge machines and they shear the rock and they measure the angle of friction, and that's maybe not so important as the rupture process itself. Just as an aside, while Zed was here, Uwe Reimel took him to the Vredefort Dome, and there he took some measurements, and it landed him another paper in Nature. Basically, what they did, they measured the angles of these shutter cones, and they calculated that because the angles increase, the velocity of rupture propagation divided by the velocity of the Rayleigh wave decreased. So the velocity decreased as distance from the impact increased. And that was a quite nice little paper in Nature. Okay, now we look at the seismic displacement. So where you do have these large displacements close to the mine openings, you have up to 100 millimeters displacement with events of magnitude 2.5 and so on. This I need to go back. Okay, I think I missed a slide here. I'll come back to that in a second. So there's an example case which I managed to map. They tried to go through the dike. There was a burst damage here. So they eventually went through the dike. You can see the stope face there. And then from there, they up-dipped along the dike. And I could measure, and there was an odd-tip shear along that contact. And I could take measurements at different positions numbered there, 2, 3, 4, 5, 6. At 3, for example, 70 millimeter displacement, you can see the shear is actually not in the dike. It's next to the dike over there. Another case up to 100 millimeters displacement at site number 6. At site number 4, this is what it looks like. There's the displacement. This is what the shear zone looks like, quite complicated. If I then color it in like that, and I go back to a stage when the face was at site 4, this is what you see. So these guys are drilling into the source of a magnitude 2.5 event. So we go back to Totona. Now we're looking at these structures over here. This is the initiation of the seismic event. First odd-tip shear, then the total collapse associated with more shearing. And there you can see a very nice Horst and Graben structure with some significant displacements. And these are all dynamic, happens in an instant, you know, at the velocity of most likely 2 meters a second. That slip velocity is about 2 meters a second. The rupture velocity is close to maybe 2,000 meters per second, 3,000 meters per second. But the slip velocity is around 2 meters a second. You can see the beautiful odd-tip shear there, displacement, and so on. Okay, there it comes. So, McGard picked up on this, and he wrote a paper which he called, that was a original paper by Nick Gay and Ortlip. He wrote a paper, The Anatomy of Mining-Induced Faults Revisited. And he basically pointed out that the 100 millimeters displacement is too much, not for that magnitude. He was at the same time likely working on this paper, in which he and his co-author Fletcher claimed that the maximum displacement along an earthquake is proportional to moment cube root of moment, which translates to that number, 0.0046 times the cube root of potency. Now, potency is the volume of the source times the strain change in the volumetric source, Or if it's a planar source, it's the area that slipped times the average displacement. So you can see the units of potency is cubic meters. And if you want to go from cubic meters to seismic moment, you multiply with the rigidity which you thumbsuck. You don't know that. And then from moment, you can use the Hans-Kanamori moment magnitude and come to magnitude. And we'll get to that in a second. So basically what he says is that 100 millimeters displacement is simply too much, cannot be. So we take that data, we say there's your potency. If we then say that if the average stress drop for mining-induced event is 1 megapascal, and we assume that rigidity is 30 GPa, then we can calculate the average strain change at the source as 10 to the minus 4. And from there, you can go to the volume. If you know what the strain change is, you can go to volume, and you can estimate for every potency, you can estimate the source radius. And from that Magar equation, you can calculate the maximum displacement. So that gives you some numbers. So from potency, you go to magnitude, source radius, and it gives you some idea what's going on. So if we take this and we go to historic measured displacements along faults and bottom shears, we can list them like that. All of these were structures where the displacement was measured. And then you divide the measured by the estimated from the equation of, and then you get a ratio. And you see all the ones where that ratio is wrong are all bottom shears, okay? Where that displacement is too large for the magnitude. While the earthquake-like events are okay. Now, just a quick explanation of that. Let's take a stope and we have a pillar in the stope, and we take out the pillar in one go. We fail it. So the pillar completely collapses. The stope closes dynamically. So now we have the seismic source volume. There's the source volume of the seismic event. And you can see it has a particular size that determines the magnitude. If we take the same stope, but now we allow it to close and we mine in that direction and we put backfill in and all of that, you end up with that size opening. Then you have an OTEP shear there. And now that is the source volume. But because of the softness of the system, that OTEP shear now can have 100 millimeters displacement. That means this estimation of Dmax from potency or moment in the mining environment is simply not sensical. It just doesn't make sense. You don't bring this pure earthquake seismology theory to the mines where you are dealing with mine openings, and all that nature wants to do is close that opening. It's a different story from what you have in earthquake seismology. It's closer, in fact, to the seismology you get around volcanic environments. In volcanoes, you get volume changes and things like that. Okay. I think I should stop here because I have another section on faults, but I won't have time. So let's stop and we can have some discussion.
Thanks, Gerrie. That's excellent. Lots of good stuff, particularly for the mathematicians amongst the audience. I don't know if you can see the chat box. There's been a couple of contributions and an interesting question by Elisabetta. Elisabetta, do you want to ask the question directly and get the discussion going? Can you see it, Gerrie?
Yes, I'm wondering if the seared tacklites always contain melt or something is just cataclastic rock. Yes, that's a good question. And there's some, not always everybody agrees on that. I remember Zef not being convinced that some of the structures we see on the ground are pseudotachylites. He was talking about ultracataclasites. But the original pseudotachlite, I'm sure, was a melt. So, and obviously you're going to have everything from a pure melt, or not a largely molten material, to something which is ultracataclasite with maybe droplets of melt, depending on the pressure temperature conditions under which that dynamic deformation takes place.
Okay. Other questions? Gillian, you also put a document in the chat box. If you send it to me, I'll send it.
Look, if you look at the extreme example is pillar failure. Now we're talking about the seismic theory, the seismic moment, and so on. There was a magnitude 4 event. It's somewhere, maybe in a potash mine. I think it was Kazakhstan or somewhere. This described, I don't have the reference now, but it was a massive event. Magnitude 4, earthquake, boom. And there was no shearing involved whatsoever. It was simply the collapse of the mine. If we had seismic records of Coalbrook, it was a pillar run. The total moment would have been huge because we had a huge stope closure. So, a seismic event is a non-linear feature, and rock deforms. There's rock deformation, and it's dynamic. When that deformation involves the closure of an opening, you get a lot of moment. Sometimes not much seismic radiated energy. The energy, to a large extent, comes from the friction. You can have two faults. One soft and it slides slowly, and you have another fault and it slips fast. They can have the same displacement, so the same moment or same potency, but the rate of displacement then determines the energy radiated. And then you can divide energy by potency, and you get something that's called apparent stress. And apparent stress then is a proxy to the stress, the shear stress active on the fault during the seismic event. In that way, you can map out areas which are highly stressed and less highly stressed based on the seismic data. I hope that kind of addresses your question, Gillian.
Yes, thank you very much, Gerrie. I just typed something into the chat box, and there is a theory. We do observe earthquakes which are non-shear, which apparently the sources can only be explained if there's opening or closure of cavities. I actually worked with Art Magar to some extent on this. I was publishing one stream of papers, he was publishing another. But having said that, there are certainly observations out there which suggest that a lot of crustal deformation is aseismic, maybe 95%. So yes, I'm not disagreeing with you whatsoever. I'm just kind of
but aseismic is aseismic. If you ever get the opportunity to go in a potash mine, which is where the country rock is salt and it's creeping like crazy, those stopes close like within a couple of days. Hold your ear against the sidewall, and you will hear something like Rice Krispies, snap, crackle, pop, as these individual crystals of these coarse halite are fracturing, and the rock is creeping. But on a particular scale, it's still dynamic. So it is a non-seismic, because you call it non-seismic because your instrumentation cannot record it. So in seismic events, you can have slower and slower and slower earthquakes. The slowest of them, you need a particular ultra low frequency instrument to measure it. And then you get to a limit where your instrumentation cannot measure it anymore. So whether a deformation is seismic or non-seismic depends on the instrumentation that you use to measure it. Simple as that.
And Gerrie, how deep was the potash mine? Sorry to cut it.
Not very deep. Maybe 200 meters, 300 meters.
Okay, it was interesting. I mean, Coldbrook was a shallow.
Yes. Yeah, I don't know of any seismic recording of it, but that would have been a massive, because it's a massive closure. The volumetric closure was huge, but it was over minutes. Okay. We have an example of a pillar run at the platinum mine that took weeks. Okay. So it's all a matter of the rate of failure.
Yeah, I mean, we tend to get hooked up and say, well, you know, these things happen in deep gold mines and be careful, but actually they can happen anywhere, what you say.
Absolutely. Our current platinum mines are not immune. There's lots of activity there, and they're not so deep.
And Neil Phillips, who's on the talk, has got a question in the chat box as well. I mean, Neil is a very experienced gold geologist, so he's keen on, you know, getting the ore out, but he's also got a question for you there as well.
Just about Chris Rudding. I was still at university when he came to give us a talk, and he was talking about how they are experimenting with non-explosive mining, where the stress, using the stress so high that the rock fractures by itself. And then they started using just hammers to hit the stope face so that it will mine itself. And later on, I used some of that data I was tasked to compare seismic hazard between explosive and non-explosive mining. And it turns out that the total hazard remains the same. Doesn't matter how you mine it. You make a hole, the nature wants to close the hole, and that creates seismic hazard. And whether you mine it by hand or mine it by explosive, the total deformation is the same, and it doesn't help you in terms of seismic hazard.
Good point. And respect of Neil's question, and I guess one of the factors too, and you'll know that better than me. I mean, you know, there's a hell of a lot less mining these days in the
look, the statistics. If you look statistics. If you look at the Rockburst fatality statistics over the past 20 years, the trend is downwards. If you normalize it by production, it hasn't improved over the past 10 years.
Yeah.
If you normalize the fatals and the Rockburst frequency to production, then the Rockburst risk is still the same. It hasn't changed. And there's only one way that I can see. So that the question is, are there still Rockburst still a major risk factor? Absolutely, it is. It's just we don't hear so much about them. Why? Two, yes, compared to 20 years ago, it's much better because of what I mentioned earlier, the stiffer systems that they design by mine design. You allow less closure, and you lessen the hazard. But that has a limit, because eventually it becomes uneconomical to mine. You leave too much rock behind, and then there's just simply not enough money coming out. So there's, and we've reached that limit now, I think. So you cannot make it more stiff. And currently there are two things that limit the fatal accidents. The one is limited mining. Secondly, luck. There's a lot of rock bursting taking place which are not reported, because that if you report it and there's and someone goes to investigate, it holds up mining. I mean, this hasn't changed over the past 100 years. It's still the same. They will not make. Of course, we know about it because we can measure it. We have the seismic data to show it. But if it's not reported, it's not investigated. It doesn't interfere with production, and that's it. And only when there's an accident is it properly reported.
And Gerrie, just again a question, specifically on the gold mines. I mean, how much research is still ongoing? How many of these institutions exist? And I mean, I know people like Ray Durham will be involved. But the feeling is very little.
I think the problem is mainly money. There's currently an attempt, again, another attempt to do some research to improve mindset, to limit Rockburst hazard. But we're talking about a couple of millions a year. I mean, total budget of maybe 5-6 million. If you want to address this problem, you need billions. You need to go in there and take a stope, take a mining environment and bring in technology like hydrofrack and frack the whole world. And that's going to take 2 years of fracking and then mine the ground. So there we talk millions and millions of investment and research. And then you get somewhere. By just taking more data, what kind of research can you do now? You have masses and masses of data. You analyze it and analyze it and analyze it again and again. The Rockburst problem is not solved by research into seismology. It's solved by engineering. Mining engineers should solve the problem. And engineering research is much more expensive than taking a lot of seismic data and do statistical analysis of seismic data. So I think that the problem is the direction and the funding. And that's where, I mean, these two guys, Sabanya and Harmony, they can't wait for research. They're going to do it themselves. They're going to hydrofrack the pillars, or they're going to blast the pillars and see whether they can soften them to mine them. And these classic research, Comro, old Mining Tech, or Minerals Council, or whoever has some money, they're not going to scratch the surface. You need some real decent mining engineering work done.
Yeah, I mean, that's the tragedy, and it's in every facet of our mining exploration business. We're just not spending enough. We don't have enough smart young students doing good research to drive this whole process forward.
There's a question on the rock type. In our case, in the gold mine case, the rock type along the stope doesn't vary much. The rock type away from the stope, above or below the reef, does vary, and that changes the nature of the seismic hazard to some extent, depending on whether you have a soft hanging wall or stiff hanging wall. So that does change the nature of the seismic events to some extent, but not overly so. So we find that, of course, with our numerical modeling, it's difficult to, unless you use very high level code, domain method code. If you use the normal elastic codes that we use, you cannot accommodate all these small subtle variations. But we find that in practice, you don't really have to. Rock is a funny thing. When it deforms quickly, you can treat it as an elastic material. When it deforms slowly, you have to treat it as a plastic material. And in our line of analysis, we deal mainly with the elastic component. So only, of course, the stope closes behind you. That's non-linear. But dealing with the head of the face, the rock mass head of the face, you treat it as elastic, and then you find as an elastic material, different rock types do not behave so much differently. What is important is dikes. When you get towards a dike, the dike is a bad thing because it's much stronger than the quartzite, and it can for the same load that you have on the dike, the dike is more highly stressed. The stress inside the dike is much higher, so it can explode on you. So dikes are very important in that sense.
Thanks. Okay, any last questions from the audience? I guess, Gerrie, then just to say...
Yeah, there's a question about groundwater as a lubricant.
Okay.
There was a case, Mining Tech tried to pump water into a fault. And that's not a good idea. Because if the fault wants to give you a large event, it will be hung up. There will be an asperity holding the fault back, and when that asperity fails, you have an earthquake. Now, when you start pumping water, the water goes to the area of low pressure, not into your asperity. It's not going to help you. But what you can do is soften the rock mass around the fault. So you hydrofrac the whole rock, not only the fault, you hydrofrac everything. Then you soften the whole rock mass, and in that way, you limit the dynamic deformation.
Thanks, Gerrie. Any last questions? And just to comment on Richard's point, I mean, I think, and Gerrie, you will have known, just about all of them. The characters in this business were just amazing people, wonderful scientists, obviously, and engineers, and I think there were a few odd ones amongst them. You'll know them, but again, wonderful characters. I mean, my family, we had a wonderful long association with Dave Ortlip, and his brother, interestingly, was a coal geologist at Anglo, also a very good guy. And Dave taught me to trout fish. As you know, he lived trout fishing. Yeah.
He was a fantastic tutor, and I used to carry his cameras, and he had a whole suitcase, and so we used to heat them up in the winter. We used to, in the changers, heat the cameras up. These were still film cameras. And we used to heat them up with the heater in the changehouse, and then roll them up in T-shirts and put them in our bags. And he had a suitcase with his camera equipment. And of course, since he's just out of politeness, I had to carry most of the stuff. And so I carried these cameras for many miles underground. But he was such a great character.
And I must say, probably the most patient man I've ever met. As you say, he was a wonderful mentor and teacher.
Yeah.
Okay, thanks everyone, and thanks, Gerrie. And we look forward to another presentation next week by Alan Guest. And again, it's an interesting one. Us geologists have always also had problems with mining engineers, and in this case, Alan's going to talk about breaking diamonds with explosives, which obviously is strictly a no-no, but it happens, and we look forward to that presentation next week.
Dave Arnold has requested that, going on from last week's meeting, where we were talking about the seismic events and the was it Gerrie van Aswegen? He'd like to just add a little bit to that, and so that we can have it part of the recording. Off you go, Dave.
Okay. I'll try and keep it as brief as possible and not get into Alan's time too much. But I just want to sort of compliment Gerrie on a job well done last week. It was very long sort of range of history that he managed to condense very nicely into the talk. And it just reminded me of when we started. The guys that he spoke about were mainly mathematicians and so on, and they come from very, very long ago, starting with Pinky Hill and people like that. But when practical rock mechanics started in South Africa, it was around about half a century ago now. and I can't believe it's that long ago. A lot of the practitioners that first started were attracted to the discipline from geology. They were geologists. They were people like Phil Reeves, who fortunately was killed in Angola. And then Dan Klutter, who was the, and he would know very well, who was the champion of cave mining on Anglo-Val's Waterbeersfontein mine. And then, of course, Henny himself has started life as a geologist. And I was just wondering whether very many people know about the range of his activities. He's a modest sort of person and he wouldn't brag about it, but I think he's the only geotechnical engineer in the world who has the range, and naturally, most probably as well, but certainly vertically. He's been responsible for mines that are over 3 kilometers deep and for operations that are higher than 3 kilometers above sea level, in South America and here in Lesotho and so on. So his range is in the region of 6 kilometers, if not more, and it's, I think, very, very few people will ever be able to sort of equal, never mind better, that achievement. So well done, Henny. Gerrie spoke about the development of fractures associated with high stresses ahead of the face, and he talked about the Dave Ortlieb or Ortlieb fractures, as they've become to be called. But I just want to say that a lot of seismic activity in the deep level mines is associated with pre-existing discontinuities, things like dikes and faults and those sorts of things. So, there are a couple of strategies that the mines have put into place, and the first of those is to reduce the percentage extraction by leaving strike stabilizing pillars. And the idea behind that is to reduce convergence, which then reduces the amount of elastic strain energy that is stored ahead of in the solid areas ahead of the working faces. And that can be achieved by backfill as well. And the other strategy is to leave pillars adjacent to the discontinuities like faults and dikes, so-called bracket pillars. And the idea behind that is that the normal stress across those features won't be reduced, and then minimize the amount of slip and movement that can take place across them. As an example of that, I measured about 10 inches of slip, and this is recent slips, co-seismic slip on the Dagberg fault, and that sort of traverses the Welkom gold mines and was responsible for a block of flats falling down there. On Ellen's I noticed that most of these fractures are lined along dip rather than along strike or any other way. And it occurred to me that we could perhaps combine the bracket pillars with the stabilizing pillars. And so I had a chappie that I imported, one of the guys that I imported from America by the name of Dan Applegate, and I got him to do the necessary work and so on, and he managed to get an MSc out of it, and arising from that method of mining was introduced on Elmsrod gold mine very, very successfully. In fact, it spread to other deep level mines as well, and the sort of new mines that are still on the drawing boards, as it were, use this sequential grid mining. And the only thing that I can't sort of claim credit for is the name. The name was given to it by Terry McCarthy, who was the planning official on Elandsrand at the time. So having those kinds of strategies still didn't eliminate the hazards of rockbursts and so on. So Van Zyl-Brink and his guys on Western Deep Levels were involved in trying to predict seismic events, and they had little what you call microseismic network, which they did. And perhaps if I can draw an analogy, if you can imagine that the screen that you look at right now is your working place, like Gerrie showed the photograph of a couple of drillers in the face drilling into the face. Okay? And just imagine that your workstation where you are right now suddenly explodes with forces approaching sort of small nuclear proportions. It's really unbelievable. The only way that you'd be able to avoid being wiped out as your screen exploded and the roof collapsed and the ceiling came down and so on, was to have some sort of warning about what was about to happen. And if you could give sort of 5 or 10 minutes warning, you could get out into the street and watch your house implode. Or in the case of the drillers, they could get out of the face and down into a safe area. So there was a lot of push on trying to establish a prediction technique, if you like, to do that. And for Zyl, and we actually introduced it on Western Deep Levels, and we had full cooperation from tripartite cooperation from the mining guys, obviously, and the unions and the Department of Mineral Affairs.
Dave,
yeah.
Can we cut it in a minute or so? We're all sort of juggling in a load shedding as well.
Okay, no problem at all. Okay. And so there were problems associated with that, because as soon as you pull people out of the working place, then that seismic activity and it goes down. And the analogy that I like to draw is like the weather reports. Okay, there's a lot of technology goes into the prediction of weather. They can tell you exactly where it's going to rain, how much it's going to rain, what time it's going to rain, all of those kinds of things. But you can be standing out in the middle of a thunderstorm, and with all the technology in the world, you are unable to predict where the next lightning bolt is going to strike, its intensity, and what sort of damage it's going to do. So that's basically, we after a long time came to that conclusion that we're not able to do those kinds of predictions. So we have to rely on support.
Any last comments, questions? Thanks, Gerrie, and thanks everyone. Really appreciate the attendance, and thanks, Gerrie, for a fascinating presentation.
Okay, pleasure. Thank you, guys.
Yeah, thanks very much.